The last two videos that we're going to cover in this unit are about empirical formulas and then molecular formulas. You need to know how to do an empirical formula first before we can get to the molecular formulas. So an empirical formula is just a very basic ratio. It gives you the lowest whole number ratio of every atom within the compound. It doesn't tell you exactly how many of each there are, but it just gives you a ratio. So for instance, it also may or may not be the same as the molecular formula. Sometimes it is and sometimes it isn't. Let's just do an example here. Hydrogen peroxide is H2O2, and that's a molecular formula because it's telling you exactly how many hydrogens and how many oxygens. Now that's not at the lowest ratio of hydrogens to oxygens. We could actually reduce that down to just HO, and that would be an empirical formula. So there's the empirical formula is the lowest ratio, where a molecular formula we're actually going to figure out what do we need to be multiplying by to get the molecular formula. In this case it was 2, so we would have had H2 and O2. So we're going to look today on how we can come up with the molecular formulas. A molecular formula just shows the actual elements, and it shows what types of elements, and it shows a ratio of how many to each one. For instance, in the HO example, it's always going to be 1 H for every 1 oxygen, so 2 H's would be 2 oxygens. And we're going to walk through an example with this one. Okay, so we're going to look at nitrogen and oxygen, and nitrogen and oxygen can combine in many different ways because they're two nonmetals. So we could have nitrogen monoxide, we could have nitrogen dioxide, we could have multiple combinations. And so we're going to look at an empirical formula and just get an idea of what the lowest ratio is for nitrogen and oxygen to combine. We have 25.9% nitrogen and 74.1% oxygen. So to start off, step number 1 is we want to change the ratios here, these percents, into moles. Okay, we know that we can take the percent, 74.1 grams. 74.1% means that is 74.1 grams for every 100 grams that you have. We want to convert those to moles. Okay. So 25.9 means that you have 25.9 grams of nitrogen and 100 grams of that compound. We've done that before. And so really we have we're going to stay with we have 25.9 grams, all right? And we know that with a molar mass we can convert grams to moles. So our first problem here, okay, step 1, we're converting these to moles. We have our 25.9 grams. We got that from our percent up here, 25.9%. We look up on the periodic table nitrogen and see that it's 14.0 is the molar mass. So we're just doing a very simple grams to moles conversion, which we've done before. And we're looking at our significant digits and keeping 1.85 moles of nitrogen. And we need to do the same thing for our oxygen. We had 74.1% given to us in the problem, which is converted to 74.1 grams. And oxygen has a different molar mass. It's 16.0. So we're going to be taking 74.1 times 1, so dividing that by 16, and again, 3 significant digits. So we're at 4.63 moles of oxygen and 1.85 moles of nitrogen. Now that's just step 1, okay, converting it over to moles. Step 2 says that we want to reduce that ratio to the lowest whole number ratio, and we do that by dividing by our smallest number of moles. If you think back, nitrogen was 1.85, oxygen was 4.63, so our lowest is 1.85. So we have nitrogen with 1.85 moles, oxygen with 4.63 moles, and we're dividing each one by the 1.85. When we do that, we get 1 nitrogen for every 2.50 oxygen. Now there's a slight problem there because you can't have part of an oxygen. We have to have whole numbers. So if we get to step number 2, when we divide them, if they work out to round perfect whole numbers, awesome, that's great. We can't just round that up to 3. That doesn't work. We need to Okay? If that reduction doesn't give us a whole number, then we have to multiply each one by the lowest number that will get us to a whole number. So 2.5, start off with multiplying it by 2. If you multiply 2.5 by 2, you're going to get a 5, which is a whole number. If that wouldn't have worked, then we want to multiply each one by 3. Would that have given us a whole number? So what you multiply each part by, could be different. You want to go with whatever's going to give us the lowest number, which in our case is 2. And you have to do that to both of them. So nitrogen, we take 1 times 2. And oxygen, because this is the one we really needed to fix, 2.5 times 2. And that gives us our lowest whole number ratio of N2O5. Alright, that is the empirical formula for the percents that they gave us in our problem. Let's actually go through one together then, and writing this out with me as we do the parts. So we're going to start with 3 different elements, and we're going to start with step 1. We want to convert these to moles. So in step 1, we took our percents, and we know that those are actually grams. So we're going to take our grams of mercury, Hg. On the periodic table, we have 200.6 grams per mole. And so right now we start off with 0.337 moles of mercury. Again, significant figures are very important here. You're allowed 3 because of that 67.6. Now for our sulfur, we have 10.8%, so that's 10.8 grams. And if we look sulfur's mass up on the periodic table, we have 32.1. Make sure that your molar masses go out to 1 decimal place, so don't round it to 32. We want 32.1. And again, these are just simple molar mass conversions. We've done many of these. When you divide, you'll get 0.336, and we need 3 significant digits. And then the last one we have to do is our oxygen. We have 21.6%. That's 21.6 grams. And oxygen has a molar mass of 16 for every 1 mole. And that gives us 1.35. And that's moles of oxygen. Now that's just step number 1. Step number 2 said that we want to reduce our ratios to the lowest whole number by dividing by our smallest number of moles. So in step 2, we're right now at, I almost said hydrogen, mercury, 0.337. We have sulfur, 0.336. And we have oxygen, 1.35. Now the lowest number that we have is the 0.336. So we're going to divide each of these by 0.336. And I'm going to run out of room here, so I'm going to start back up here. When we do that, the Hg becomes a 1, and the sulfur becomes a 1, but the oxygen becomes 4.02. And in this case, that is, 4.02 is 4. We can't round, 4.5 up to 5. That wouldn't have worked. But 4.02, we really are at a whole number if we're looking at that. Let's go back. So our empirical formula, in this case step 3 is not needed. Okay, step 3 might not be needed every time, just occasionally. So right now this is just our empirical formula, HgSO4. And that very well might be the molecular formula as well. We wouldn't know that unless they gave us a little bit more information. But that's how you would calculate empirical formulas.